I would like to ask Ruth Jarman of Semiconductor to the front to give a presentation about her work with the QuProCS consortium, which is about quantum physics. I'm very curious about where they are, what kind of tangible material they have produced. And after her presentation, Ruth will be interviewed by Ralph Dum, who is commissioner at DG Connect and who's an advocate of more art and technology interactions. So I'm very curious about what you have been able to prepare as questions for later. Please give a hand to Ruth Jarman of Semiconductor. And I can say briefly, there's, for everyone who's very thirsty, because it's pretty hot here, there's a new water container that just arrived. So there's water around the corner. I don't know about coffee.
Okay. Hi, it's great to be here and really interesting to hear how all the artists are developing with their projects, because we had a meeting a few months ago and things were in even earlier stages at that point. And me and my partner Joe Gerhardt, who work together as Semiconductor, we're still very much in the research phase. And today I'm just going to talk for about 5 minutes on a bit of the overview of the team that we're working with and some of the ideas that are coming out of that, and then our approach to how we research. So we all know that quantum physics is a very tricky subject to try and tie down. To try and create or to try and engage with it or understand it in some way, we have to try and let go of all of our experiences that we have in our classical everyday world. So things like certainty, that we know exactly where objects are going to be in space and time, or things like cause and effect, or even our just everyday sense of reality. So our first engagement with thinking about quantum physics was last year, when we spent a few months at the CERN Particle Physics Laboratory in Geneva. And every week we would have what we called a therapy session with this theoretical physicist, where we would go and try to interview him about theoretical physics. And he would always start off by telling us, you know, if you think you understand quantum physics, then you don't, because nobody does. And so the talks would pretty much carry on like that, and he would always try to pull the rug from under our feet by saying things like, you know, time goes forwards and backwards, and then, you know, try to have these discussions about these things. And I think he was really trying to prepare us for the journey that we had ahead. As Dimitri and Evelina said, you know, it's a very complex world to kind of go into. So for our FEAT residency, we're also working with quantum physics, and we're working with a team called QuProCS, which is the quantum probes for complex systems. So it's a very similar field to Dimitri and Evelina, but they're working with quite different technologies. So the combination of FEAT and CERN have been our first experiences of working with quantum physics. In the past, we've worked with many other fields of science. We've worked with solar physicists in a NASA Space Sciences lab, with mineralogists at the Smithsonian Mineral Sciences lab. We've worked with seismologists and volcanologists, and we're very interested in the physical matter of the world around us and how scientists look into that. So we produce mainly moving image works, and this is an image from one of our pieces called 20 Hertz, where we worked with data that had been collected from a large array of magnetometers in North America, and then we worked with that actual data to turn it both into image and sound. So we're interested in how the matter that the scientists are working with, but mainly the techniques and processes they develop to understand that. And we're interested in the kind of signature that brings to science, and perhaps how that ends up mediating nature, what it brings to nature. So, you know, our work is very visual and audio-based, and it's not lost on us that the realm of quantum physics is very difficult to try and understand, let alone create an experience of in some way. So we're really up for the challenge of trying to create our own interpretation of quantum with the research that we're doing at QuProCS. So the team we're working with is QuProCS, the Quantum Probes for Quantum Systems, and it's a joint project between about 5 or 6 laboratories across Europe. We've made 2 visits to 2 of the labs, and then we have another one coming up in October. So we visited the Clarendon laboratory in Oxford University in the UK, which this is an image from, and also Strathclyde University in Scotland, and then we'll be visiting the Turku University in Helsinki in October. Both labs we've visited have experiments in situ, so this one is from the Oxford University lab, and to look at them you'd think they were very similar setups. To explain it very briefly, they, to simplify their science down to a few sentences, they basically are working with lenses and traps, and they send 2 lasers, so 2 light beams through these many sensors, and you're probably familiar with images of these kind of setups where there's these kind of complex networks that drive the beams, control the beams, split the beams, turn them into different frequencies and do all this fantastic stuff. And then at the end, they bring the lasers together and create what they call a lattice. And this is one of their kind of classic images of them creating a lattice. So the beams come together, and in the beams, they're controlling a cloud of atoms. So there can be tens of millions of atoms in this cloud, and they are trying to control those atoms individually. And the image they always use to kind of try and visualize this is an egg box. So you have these troughs and peaks, and in the troughs, they try to place one atom, and they're just at the stage where they can actually, using the lasers and using magnetic fields, they can transfer one atom into another trough and start controlling the system. So the use for these simulations is either to try and observe the phenomenon in these quantum systems themselves, or use them as emulators, so quantum simulators, so they can introduce physics, less well-known physics, and then observe that within a quantum system. And QuProCS' specific goal is to, this is the future research part of their project, is to try and probe or extract information from that quantum system. So it's well known within the quantum physics that if you try to observe the quantum, you destroy the quantum state. So, for example, you can have a particle that exists everywhere all at once in the quantum state, but as soon as you take a photograph of it, for example, then you locate it, you fix it in space, and then it becomes back into the turns back into the classical world, so that you're fixing the object in space and it is no longer a quantum space. So they're trying to develop a way that they can actually extract information without destroying the quantum state. And this probing is at very, very early stages, where Anna was talking about that the FEAT projects are actually 4-year-long projects. We come in at the beginning, and they're still really kind of dabbling. That's not a very positive way to describe it, but they're still dabbling with the quantum simulation stage. So, you know, they fail a lot. They don't very often successfully produce these quantum simulations. So there's 2 images which give a sense of the kind of what we call the science products that they're producing as a result of these images. This one is an image of one of the quantum clouds, and you can see the kind of lattice formation, the shape that it's taking. So that was a successful quantum cloud, so a quantum simulation. And then also we've been working with some of the computational simulation scientists at Strathclyde University, and they're producing data that can be mapped, which is they're producing actual quantum scientific data. So our approach to research is really just to throw ourselves in the deep end and just figure out what's going on. You know, we have so many interests, and then we start narrowing things down. we've been looking at, the tools that they use and the hardware. So looking at all these lenses and the lasers and how they actually control this stuff. We've been thinking more about the fundamental properties of light and matter and learning about the quantum electrodynamics theory, one of Richard Feynman's theories that he got the Nobel Prize for. We've also been working with Anton at Strathclyde, who does the quantum computer simulations. And, looking at all the theory and all the stuff that comes out of there. So one line of thinking that we've been exploring is how to create, and there's been a lot of talk around this today. I think Vicky and Paul are trying to leave this behind, and we might just be entering this phase of creating our own quantum computer-generated simulations. Now, of course, we're not trying to calculate quantum simulations because that's nigh on impossible. Really, you need a quantum computer to be able to handle the amount of information and the complexity. But we're interested in trying to create our own 3D generative models that have the characteristics of a quantum system in them, and then combining this with the tools that they use to represent the computational simulations. So the way that the theorists, over the past 100 years have been developing formulations, basically equations with mathematics, they create these to understand, say, one tiny part of a quantum system. So it might be to explain the dynamics or the topological information or local and global properties. And we're looking at these formulations and thinking about what characterizes them and using the essence of those things. And at the heart of these formulations is the idea of probability. So that will really drive the work that we're thinking about doing. And this is one of many ideas that we're thinking about. So, we really want to explore these theoretical models and the computer simulations as tools and as language. We're interested in finding out the human, or revealing the human signature within those things, as a way to understanding what man brings to nature. So are we really experiencing nature, or are we experiencing science? Is science just mediating nature? Okay, that's good. And I'll just finish by saying that a solar physicist once said to us that science is just a human invention, it's nature that's real. And for us, our main interest is at this point where nature and science meet.
Thank you, Ruth. Please, Ralph, I'm curious about what you are going to ask Ruth.
Yeah.
There's a second microphone. Yeah.
Yeah, so while I was trying to understand what I would ask today, I was looking at what you are doing. I realized actually that I've seen an artwork of yours, but I didn't have to apologize, associate it with you. Only yesterday evening it occurred to me. So there's this work called Earthworks, which I've seen in Barcelona during the Sona Festival. And I have to say I was rather fascinated because it is...
we don't hear you well.
It is a work that... that immerses you in the field of tectonic movements, right? So it is some sort of making an experience out of seismic data. And I found it rather interesting to see that big data was mentioned in the previous presentation, how artists can make out of data, seismic data, which are not the most sexy data on Earth, right? Out of seismic data, you made a very interesting experience, bringing together the seismic data, visualizing them, but also creating a soundscape. So I thought this is a very nice example how art would take up science. And I was wondering if you want to say something about how you came about these ideas?
Yeah, the way we worked in Earthworks, using the data to make the image and the sound, is something that we've done in a lot of our work. And for us, it aligns with what happens in nature. You know, Earthworks is a good example to talk about, because with seismic data, it exists as a wave that obviously you can potentially see quite often in the aftermath of an earthquake, for example. You can see waveforms across the landscape. But, you know, it's also something, because it's a waveform, you can translate it directly into sound. So we're not talking about sonification, where we attribute human ideas of musicality into something, but it's actually a direct translation into sound because it already exists as a waveform. And we're interested you know, in how our senses can transcend those kind of boundaries. And it's been in our work since the beginning. We started working with computers, and this idea of kind of the material, being true to the material, like Anna was talking about. You know, as an artist, when we first started working with computers, we were like, well, what is the computer? What can we do with it? What is its materiality? What can we do? And, you know, we reduced everything down to the zeros and ones, and we made several pieces of work nearly 20 years ago now, which are exploring zeros and ones, that they can represent both sound and image at the same time. So it also stems from that interest of kind of how you can represent sound and image, that they're tied together, not just synchronized, but they're from the same thing.
I've seen another work of yours, which is, I've forgotten, A World in the Making. And you made so this is essentially about your interaction with volcanologists. And then you created again an artwork out of it. But you made an interesting statement in some of the descriptions. You said, we wanted to understand the ultimate constituents of matter in the most simple way. And now you move on to CERN. And you will see a very different way of ultimate constituencies. So, and also in quantum, of course, we were talking about quantum now. So this is a very different way of approaching science. Do you see a link between this World in the Making project and your work? By the way, congratulations for your collision at CERN prize, which is very interesting. So you didn't go there yet, I suppose.
We did, actually. We were there.
You were already there?
This time last year we were there. And we spent so from October we went there for 3 months. But we haven't made our work from being there yet, because we did the Earthworks project. And actually that time frame, in a period of a year, which we carried on doing our research, you know, it was so involved, just so much stuff to process. We are now at the point where we're about to start making work, and I have so much more of an understanding about how we want to approach that now. So the benefit, again, of working with things over a much longer period of time, I think, can sometimes mean that you produce better artwork as a result of that.
You talked about the human touch just in your presentation. So the human touch in Earthworks seems very clear, right? And it was very clear in being immersed in your installation. Yeah. The human touch in quantum is less obvious to me. Do you have some idea about how you would achieve that?
Yeah, it's really interesting. We are, well, in terms of CERN, we're actually... the day before we left, we convinced the Atlas team, which is the biggest experiment there. We'd spent the whole 3 months, this was kind of our sideline project the whole time we were there, trying to convince the scientists that it's a really good idea to give us data to work with. So the raw data, because all the stuff that you see with all these diagrams of particles flying around everywhere and all these coloured lines, you know, that's a long way down the line from the raw data that they receive. So they're very cautious about revealing data to the public, because they can quite often go back and maybe find new stuff in the data, and then they also have another experiment there, and they're kind of in a friendly competition with each other. So it was quite amazing that the second to last day, somebody actually said, yes, you can work with the data. So we're working with, in that sense, with something quite tangible that has been gained. You know, it's quite difficult from the project that we're working on now, what they're doing at CERN, because with QuProCS, they're creating these quantum systems. So it's kind of, you know, it's a simulation of the quantum, but the CERN, they're extracting information from the quantum, or trying to understand the effects of it. So yeah, there's two quite different things kind of going on there. And QuProCS, I think, is definitely much harder to create some kind of experience. It is a really big challenge. Yeah.
So, normally I shouldn't ask you the question, but I do anyway. What do you think scientists would expect from interaction with you?
Well, I think expectations have changed over the years. I think with when we first started working with scientists were very puzzled about why we would want to work with their data, you know, but they'd kind of go along with it sometimes. To the point now with QuProCS, it was quite interesting that one of the scientists said to us, oh, so Sabrina said that, you know, whatever you produce, we can work with and show to everybody to explain our science. We were like, well, it's not quite what we do. And actually, you know, and then that's a kind of pressure on this. We've had to forget that because that isn't obvious. That, you know, it takes a while, I think, for those relationships to emerge, and they don't clearly happen for us anyway during the actual project of working with a scientist. It can happen a much longer period afterwards. For example, the piece of work that's on the front of the FEAT information leaflet there, a piece of ours called Magnetic Movie, we made in 2005 after being at a space sciences laboratory, and the whole time we were there for 6 months every day, and the whole time we were there, the scientists were really confused about what we were doing there and really suspicious, but we managed to interview some of them and they'd go along with it. And then it wasn't until about 5 years later that we actually went back to the lab, and their attitude to us had changed so completely because the work had been out there, it had been exhibited in spaces that they kind of had a high regard for, and they'd had people coming back to them who had seen the work, so they understood that the work could be far-reaching. And even though, like one of the scientists we worked with on that, he is describing magnetic fields, and when we showed it to him, he said, yeah, he said it's almost accurate. And we were like, oh, he hasn't got the point. But then he had scientists contacting him that he works with in other labs, NASA labs in the US, saying, oh, we didn't know you'd done these experiments. And so that, you know, it's throwing up kind of questions around what they're doing.
But the magnetic fields in this movie are based on some models, or they are artistic recreations? Or?
They're artistic recreations to the extent that scientists, they actually represent planetary magnetic fields and interplanetary and solar magnetic fields and magnetic fields on Mars. And they've collected actual data from these places. So, for example, they have a satellite going around Mars and it will be capturing magnetometer data, and then they can plot that actual data. But they use all these masses of lines to represent the magnetic fields, where, of course, already they are kind of creating their own mythology about what a magnetic field is, because a magnetic field is everywhere all at once. It's not just a line in space. So people start thinking, oh, it's a magnetic field. And, you know, so we're playing with that kind of language. And I don't know, I think, to get back to the question, I think it can take quite a while for what the scientists get out of it to emerge. And they're quite used to having a very clear idea from the beginning about what their objectives are. But as an artist, you know, you're starting at that point where they're clear and you're totally unclear, and you go through your research period.
So is it fair to say that scientists want you to enter at the very end of the process, and you are interested to be throughout the process?
And I think it's important to, for us, it's important to go in to a project really naive, so that we're not trying to go in there knowing everything about the science, but we're learning it from the tools and processes that they're using, so that it enables us to interpret it in a different way and have a different viewpoint about what they're doing.